So I thought what I'd do is just quickly review a couple of the things we talked about last time and then finish up on reactions of mainly carboxylic acids and esters, but other related compounds. All right, so one of the reactions we talked about last time was Fischer esterification, which is the most common way of making esters. It requires an acidic medium. And in a typical Fischer esterification, let's just make up a carboxylic acid. You'll take a carboxylic acid and you'll dissolve it up in some alcohol. Nearly always that alcohol is going to be ethanol or methanol, though it doesn't have to be. But this is very rarely done with large alcohols. It's usually a small alcohol. And then you will heat the reaction in the presence of a catalytic amount of some strong acid. Sulfuric acid is very common here. It might mention sulfuric acid, but it's not the only one. There are others you can use too. And the major organic product will in this case be the corresponding ester that you get by condensing the carboxylic acid with the alcohol. So in this case, since we're using alcohol, we'll get the ethyl ester. And the OH group in the carboxylic acids, the OH group in the carboxylic acids winds up in a molecule of water. Good. So this is just one example of a Fischer esterification, right? I just made up a carboxylic acid off the top of my head, and I picked an alcohol at random, so to speak. And that's just an example. We also said that esters can be hydrolyzed, which is the reverse reaction. Yeah, thanks, COVID, Nobel Day. Yeah. I think some of you might have gotten to see her in one or other of these exams, but ester hydrolysis or saponification is the reverse reaction to all this. And this now can be done in either acidic or alkaline solution. And we also made the important point that that Fischer esterification can only be done in acidic solution. Why? Because if you tried to mix all these things up in base, all that would happen would be the base would pull the proton off the carboxylic acid, since it is, after all, an acid, and that would be it. Nothing further would happen. So you do need to use acidic medium. Isn't it like reacting anhydride or acid chloride with alcohol? Yeah, that's another way of making an ester. Those, though, are also, candidly speaking, if anything, in slightly acidic medium, because both anhydrides and acid chlorides are kind of acidic also. But ester hydrolysis, on the other hand, you can do that in either acidic or alkaline solution. So let's use this ester that we just made, maybe. Can I go CO2 ethyl? Is that all right? And you can use dilute aqueous acid. So again, H3O plus meaning that there's a lot of water present, right? H3O plus implies that water is also present. Or you could do this under alkaline conditions. You could do this in two steps. At first, you would want aqueous sodium hydroxide or potassium hydroxide, or it may even just say OH minus, because the alkali metal cation doesn't play any role here. It's just a spectator ion. And then you will need to do a dilute acid workup step, which the role of this acid is different than up here. Here, it's actually doing the hydrolysis also. Down here, it's first of all neutralizing any leftover hydroxide. We got to kill all that off first, and then it will start putting the proton back on the carboxylate ion that we get. And we went over the intermediates the last time. But in both cases, you'll wind up with the component carboxylic acid, CO2H, and the alcohol. So both of these do work. And actually, base hydrolysis of esters is something we talked about way back in chapter 15, I think it is, when we talked about lipids and we talked about making soaps, at least the old-fashioned way, by saponifying or base hydrolyzing triglycerides. So you get your glycerol back, that's your alcohol essentially, and you get your 3 fatty acid molecules. And actually you get them out as carboxylate salts, either CO2 minus Na plus or CO2 minus K plus. And that will mean that you get, if I remember correctly, was it the sodium salts that were solid soaps? I think so, and the potassium salts that were liquid soaps. I could have that backwards, double check me on it. Good review for the final exam in any case. But these were some of the reactions we talked about last time. And I think that's all I really need to say about that. Basically, today I want to continue on with what's called ammonolysis of esters, although this is a strange way of spelling it, the way your book does. We'll also review our old friends, lithium aluminum hydride and sodium borohydride. You may recall we said those two reagents for ketones and aldehydes are interchangeable. It doesn't matter which you use. For carboxylic acids and esters, they are not interchangeable. So we'll go over that. I might have then a few words about amides, although I think we've already talked about them a little bit. And then I think that will be enough for today. If there's any time left, we'll use that for our reef session. And also, if there's significant time left, which knowing me, there probably won't be, but if there is, I can always make up a couple of problems. Good, so your book spells it, I would spell ammonolysis of esters like this. Well, I know why they do it. Here's how they spell it. Ammonolysis. I was thinking to spell it AMINO, ammonolysis, like that. But the reason they're using this term is they're trying to make it clear that it's literally ammonia that we're using, NH3. So I see why they do that after all, I guess. And this is a peculiar thing about esters and amides, and tells you about the relative reactivity of them to some degree anyways. And the idea is that if you take any ester, I'm just going to be generic here before we go on to an example. And we treat this with either pure ammonia, or I think aqueous ammonia will also work, but I'll just put NH3 for now. The product that you will get is the corresponding primary amide. At least that's the major organic product. So you'll get NH2 over here. And you'll also get your alcohol back, which again, nearly always, this is going to be either ethanol or methanol. Those are both highly water soluble, and they'll, after your aqueous or organic extraction, they'll wind up in the waste jug. So just to be aware that you can make amides from esters, but the opposite is not true. If you treat an amide with an alcohol or even an alkoxide ion, you can't go the other way. So this is the only direction this can go. You can make you can make amides from esters, but not esters from amides. Is it a nucleophilic substitution? Yes, but it is neither SN1 nor SN2. This is a nucleophilic acyl substitution. And they're the type of reactions we've been talking about otherwise in this chapter. So yes, it's a nucleophilic substitution, but not the same as SN1 or SN2, which is funny because that's the other chapter I was thinking of dropping, was the SN1, SN2 chapter, because we did so little of it anyway. And the main place that we used SN2 was in the chapter on ethers, which I'm also thinking of dropping. So, I mean, for us, it's too late. We'll go with it, But I'm just, I'm always thinking about how to make this better in the future. Good. So just to give an example, let's say that we took, let's go nuts. Just to hammer the point home that it really doesn't matter what the ester is. Let's do a naphthoate ester. Why not? And let's say we had the ethyl ester of this naphthoic acid, or whatever it's called. I'm not even sure that's the right name. I think it's something like that. So if we were to treat this with ammonia, then we would expect to get the corresponding primary amide. All the other stuff is just along for the ride. So you would just get C double bond O, NH2. And yes, you'd also get ethanol out of this, CH3CH2OH. But this will be the major organic product that we'd actually isolate. The other would essentially become a waste product. So that's an example of ammonolysis of esters. And that's pretty general. My understanding is actually that you don't even need to use ammonia. You could use a primary amine, and that maybe R3NH2, and then in the end, instead of getting NH2, you'll get NHR3. So I think that will work too. That's why I was thinking of ammonolysis. I was thinking of spelling it like this. It's a funny thing. I literally just noticed this. This never occurred to me earlier. But this word would imply that you'll just take in general an amine. It doesn't have to be ammonia. It can be a primary or secondary amine. And so whatever R groups are attached to the nitrogen here will just get carried on to the amide. So, but I believe that's the case. I believe you can get not only primary, but also secondary and tertiary amides this way. Can we do the same thing with carboxylic acids? Great question. Answer is no. And again, the reason that doesn't work is because of the acidity of the carboxylic acid and the basicity of ammonia. So think for a minute of adding ammonia to a carboxylic acid. And I think you'll see you'll never get a chance to get any kind of nucleophilic substitution. Would there be a plus ethanol over here? Yep, yeah, you'll also get the ethanol as well, but the major organic product will be this. In any case, I think you'll see right away, ammonia is basic. That's going to deprotonate the carboxylic acid and give you the ammonium salt of that carboxylate ion. And it's then dead. It's not gonna, there's nothing else that will happen after that. So that's a good question, but yes, you do need an ester in order to do this. Does not work with carboxylic acids. And again, I think the reason is pretty clear. You'll just get an acid-base reaction. But if you meant over here, yes, ethanol will also be a side product. And the wording of the question will make it clear whether or not you have to put it. Especially watch OWL carefully. They do, to their credit, usually say what they want you to do. I have heard the feedback that my questions on exams are clearer than OWL questions, which, as I've said before, that reminds me of that phrase. It's some English poet that said it. I forget which one, whether it's Longfellow or whoever, used the phrase damning with faint praise. And I will take being damned with faint praise. Praise is praise. But be that as it may, if you read OWL questions carefully, they generally do spell out what they want you to put. Good, so that's basically it for ammonolysis or ammonolysis, however you spell it. Alex, never heard of it. I have used one other system. I forget what it was, but it wasn't Alex. It was another product. OWL's my favorite so far, but I'm sure there are better ones still. Oh goodness, chat is going crazy about Alex. I'm glad I'm not using it then. All right, so I think that's enough for that. Where are we at? 321. Let's then get back to sodium borohydride and lithium aluminum hydride and just remind ourselves of these species. Remember that sodium borohydride is the less reactive of the two. And as such, you can and generally will use it in a protic solvent. It's usually an aqueous alcoholic mixture. So this might say water and methanol. You can use ethanol instead of methanol. I think I've even seen isopropanol getting used. But it will be some small alcohol. You just need the mixture of the two to dissolve everything well. But sodium borohydride does react with these guys, but it reacts very slowly. It reacts very much faster with aldehydes or ketones, so that works. On the other hand, lithium aluminum hydride is much more reactive, and so that's why you need this two-step process. The first step will have lithium aluminum hydride now in an aprotic solvent, because protic solvents like water and alcohols react exceedingly violently with LAH. It will make hydrogen gas and also generate a lot of heat, and you can have a fire in your hands. And trust me, as much as you may think so, it is no fun. Let me move that arrow a little bit. So most often I think you'll see diethyl ether used. Something I'm always urging my Chem 227 students and 228 students also, please do not confuse ET2O and ETOH. They are completely different critters. One thing we learned in the chapter on ethers is they're quite unreactive. And so that's why they're often used as polar aprotic solvents. So ethanol and diethyl ether are completely different animals. And only then, after that, do we do a workup step using either water or H3O+. And you can write either H2O here or H3O+. Doesn't matter. But separate steps. We only add that after everything's done reacting. If you threw everything together all at once, you just get a big volcano, possibly followed by a big fireball, and you would be sad. You may think you'd be happy, but no, you would be sad. So these are the two different reagents. Sodium borohydride is a milder reducing agent. Lithium aluminum hydride is the more reactive reducing agent. And we said with aldehydes and ketones, these two are interchangeable. So either of them will react with aldehydes or ketones. All right, aldehydes. Ketones. And indeed, lithium aluminum hydride also reacts with aldehydes and ketones. Same exact result. Either of these reagents will reduce an aldehyde to a primary alcohol or a ketone to a secondary alcohol. However, being more reactive, LAH will also reduce esters and carboxylic acids. Whereas sodium borohydride will not touch those functional groups. So that's an important distinction to make. So you can see in the real world the difference in reactivity of those two reagents. So if you were to add sodium borohydride to an ester or carboxylic acid, no reaction. It would just look at each other. If you wanted to do the reduction, then you need to use LAH. So for instance, let's just get an ester going. Oh, I don't know. How about butyl butanoate, just because I can. So this is an ester, so if you treated it with sodium borohydride, no reaction. You'll just recover the ester. But if we used LAH, and again, a polar aprotic solvent like diethyl ether is very common. I almost wrote ETOH, actually. Tetrahydrofuran or THF would also be fine, any ether solvent, followed by either water or H3O+. You can put either here, it doesn't matter which. Well, what I would expect to happen is, actually, I'm now regretting this decision. Is it okay if I make it the isopropyl ester instead of the butyl ester? Because otherwise we're not going to be able to keep things straight. So let's make it an isopropyl ester. Let's go like this. I was being too cute by half. In any case, what I would expect we'd get out of this as the major organic product would be nothing other than, oops, nothing other than 1-butanol. So that alcohol comes from the carboxylic acid portion, 1, 2, 3, 4 carbons, 1, 2, 3, 4 carbons. And you also would get the isopropanol. That's going to be a heck of a lot more water soluble and would not be what we would actually isolate. But the major organic product that we would isolate in this case would be the alcohol that comes from the carboxylic acid. So that's how LAH works. And if this were a carboxylic acid, same thing. It would reduce a carboxylic acid down to the corresponding primary alcohol. So if we took benzoic acid, is it okay if I just go ditto and ditto? Then we would expect to get benzyl alcohol out at the end. CH2OH. So LAH will react with either an ester or a carboxylic acid in addition to aldehydes and ketones. But sodium borohydride will only react with aldehydes and ketones. It does not touch carboxylic acids or esters. So maybe I'll kind of end the chapter with this idea. I mean, I think there's also a section on amides, but I feel like I've already talked about amides pretty well. We talked about hydrolyzing nitriles as well as amides can also be hydrolyzed to make a carboxylic acid just like esters can. And I think I even already told you that cyclic amides are called lactams, just like cyclic esters are lactones. So I think we've said all we really need to say about those. But first I want to make sure that all of this makes sense. So any questions about that? Sodium borohydride does not work for carboxylic acids. That's right. If you want to reduce a carboxylic acid or an ester, you have to use LAH. Sodium borohydride will not touch those functional groups. And so that brings me to my next question, which might sound a little bit evil. What if we had a molecule that had both a ketone or aldehyde and an ester or carboxylic acid? Now you can distinguish between the reactivity of those two different functional groups based on which reagent we use. What would be the side product? I think you might get a molecule of water out of it, but other than that, none. So there's no alcohol over here, if that's what you mean, because we've got a carboxylic acid rather than an ester. Good, but no, that's fine. Perfectly reasonable question. Let's do this. Let's say that we have this starting material. I'm going to put on, actually, I'm going to move it into the middle for reasons which I think you'll see in a moment. Let's say that we have both an aldehyde functional group and an ester functional group. We'll put a couple in the middle. Methyl ester on this side, let's say, OCH3. What now if we treated this with sodium borohydride? And say we did that in aqueous methanol. And contrast that. Can I go back? Yes. But as usual, you can always see it on YouTube. I am recording, right? Yes, thank goodness. All right. So let's contrast that with what if we treated it with LAH? I think we would get two different products out of this. And again, I'm here talking about the major organic product, not any small water soluble or inorganic things. So we've already said that sodium borohydride will only react with aldehydes and ketones. It will not touch the ester. So I would expect that we would get a primary alcohol on that end of the molecule. I just want to count my carbons. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And the ester group will remain intact. But what about LAH? That will now kill both groups. And yes, you will get some methanol out in the end also. That's not going to be anything you'll ever isolate. Methanol is soluble in water in all proportions, but the major organic product will have primary alcohol groups on both ends with 7 carbons. So I guess we can call this guy, what about 1,7-heptane diol? 1, 2, 3, 4, 5, 6, 7. That's what I would expect to get out in the end. And yes, you would also get a molecule of methanol as well. But the major organic product that you'd isolate would be this diol, because lithium aluminum hydride reduces both aldehydes and esters, along with ketones and carboxylic acids. So in this way, if you have a polyfunctional molecule like this, which is very common, by the way, for molecules to have more than one functional group, then you can distinguish between the reactivity of those two functional groups very easily by comparing reagents such as this one. So again, the take-home lesson is sodium borohydride will reduce an aldehyde to a primary alcohol or a ketone to a secondary alcohol, but will not touch a carboxylic acid or ester functional group. It leaves those alone. Meanwhile, LAH is the stronger or more reactive hydride reagent that will reduce all of the above. Good, makes sense?